How's it going? All right, so today we're going to look at radical expressions. However, we're going to do one little thing here to wrap up yesterday's rational expressions. I kind of wanted you to practice that, get really good at adding, subtracting, multiplying, and dividing. And then what we're going to do today with it is kind of what we call complex fractions, because you're going to have to do all of that in one problem. After that, we'll jump in and practice working on all of our radical expression properties. This is called a complex fraction because you have fractions caught up inside of other fractions. So anytime it's like that, we call that a complex fraction. And so really what you're doing is you're taking this whole mess and dividing it by this whole mess. The problem that we have is we have subtraction going on in here. And I went ahead and put these parentheses to help remind you that that's all a big group because you're subtracting it, but typically you're not going to see those parentheses. So here is the process. Back to 5th grade for a minute. Here's the process. If you had something like 4/5 and you wrote it over 2/7 like that. Well, all you're doing is taking the 4/5 and you're dividing by 2/7. It's just a messy way of writing it. You might write it like this instead, divided by 2/7. Okay, and then we know that we would change that to multiplying by 7/2. All right, same deal. It's just written in a different way. So when I see 4/5 divided by 2/7, here's what I'm going to do. I'm not going to divide by 2/7. I'm going to pop it up top and I'm going to change it to multiplying by 7/2. And then before I multiply those fractions, I'm going to look to do some reducing. And then I can multiply straight across. 14/5 is my answer on that. All right, so we're doing all the same stuff with rationals. That's those same steps. So what is different, though, is that this right here is a single fraction on top of a single fraction. So you have to do that, too. You have to make this be a single fraction. You have to make this be a single fraction, which means subtracting. Let's get a common denominator. Put this over 1. Same thing in the denominator. I'm going to put that over 1 so that those are fractions. Now what I'm doing is, this is from yesterday, I'm going to subtract 2 fractions. So I need a common denominator. Looks like the common denominator is going to be an x. So I'm going to take that times x times x. So I'm going to come down below, rewrite this. This is my denominator. And my numerator is going to be 2 minus 3x. Then I have this big fraction bar, and I'm going to do it again in my denominator. Looking at, I have an x minus 1 and I have a 1. So the common denominator is x minus 1. Got to do it on the top, got to do it in the bottom, and then I end up with x minus 1 because I'm distributing this 1 here, and then it's going to be a minus 1. All over my common denominator, x minus 1. Okay, so it still looks a mess. It's still complex. It's still a fraction caught up inside of another fraction. But now I'm more at this piece right here where it's a single fraction over a single fraction. So let's pop it up and flip it. So I'm going to take this, I'm going to pop it up, and instead of dividing by it, I'm going to put a dot. I'm going to multiply by its reciprocal. So x minus 1 is on the top. And in the denominator, I'm going to go ahead and clean that up and call that an x minus 2. Now, remember from yesterday, when you're multiplying, you're trying to find something that will cancel. Like I canceled these things before I went ahead and multiplied through. Now, these are all pretty basic. There is nothing here that's identical that I'm going to be able to reduce. And that actually happens quite often with complex fractions. So then what I'm left with, final answer, is 2 minus 3x and an x minus 1 in my numerator. And in my denominator, I have an x with an x minus 2. And that's my solution. Okay, that's a complex fraction. They love to put it on the ACT. I don't know. It's just one of those things that people struggle with. So I have another example for us. All right, I might have lied. I said for us. It's really for you. It's very similar to the one we just did. So look back. Hopefully you took some good notes on the previous ones. I want you to try to do this one on your own. So go ahead and take a minute to pause the video, then come back when you're ready. Okay, take a minute, check your answer. Hopefully you agree. If not, go figure out why. I'm going to go ahead and move on to radicals for the rest of the day. When we have radicals, we're typically trying to reduce them so that we get the smallest possible number underneath the radical. We call that number underneath the radical the radicand. This right here is your radicand. And so I'm trying to get that to be as small as I can. To do that, I need to know some perfect squares to break it down to. So you should be very familiar with your perfect squares. You should also be pretty familiar with your perfect cubes. Now that we've been doing that sum and difference of cubes, those should look familiar. And in all honesty, you're going to get perfect fourth powers, perfect fifth powers. So let's jot a few of those down in the margin. Do you know what 2 to the fourth power is? That's 16. Do you know what 3 to the fourth power is? 81. 4 to the fourth power, 256. 5 to the fourth power. That one you probably typed in your calculator. It's okay. And even this one is 625. I'm probably not going to be getting that big. Definitely no 16, definitely no 81. I don't know. When you look at a 625, the fact that it ends in a 5 should sort of be your clue that, oh, that's probably the 5 to the fourth. Okay. All right, let's go ahead and let's also look at some fifth powers. 2 to the fifth power. It's really just this number up here times 2 one more time. So that's a 32. 3 to the fifth power would be an 81 times another 3. It's 243. And that's probably as high as we're going to be going. I'm not going to be doing that 4 to the fifth. So just be looking or else be able to find these values when you see a fifth root. Now, there are some properties, some basic properties of radicals. Let's go through quickly and make sure you remember this stuff. If you are taking a root and taking a power, it does not matter if you do the power first and then the root, or if you do the root and then the power. In this example, it works both ways, but in my mind, I would rather get my numbers smaller right off the bat. So I would prefer to put it like this. Let's cube root the 8, that's 2, and then square it, that's a 4. And then I'm not dealing with this 64 and my number doesn't get as big. All right, next thing, if you are multiplying radicals, you can only multiply them if their index number, that's this right here, that little number, the root, if that's identical. And I'm not going to be tricky. They're going to be the same. All right. And then what you do is all you got to do is multiply those radicands together and just leave it under the radical with that same root. So in this example, square root of 5 times the square root of 7, that's just going to end up a square root of 35. Same thing with division. It's probably going to be written like this, but envision it like this, because if these two values will reduce, we sure want to reduce them. So when I see this, I think, well, 3 goes into both. And so I would reduce that. I lied. 3 does go into both, but 9 is a better choice. 9 goes into both. So we'd divide them each by 9. And so this is going to go away, and you end up with just a 3 right there. Okay, next one's kind of a weird one. Doesn't happen a lot, but kind of a quirky, fun thing. So if you're taking the root of another root, okay, you can actually do that. And the process is simply to multiply these two index numbers, and that's your new root. So in this example, you have a cube root. This is assumed to be a little 2 here. So when you multiply them, that really ends up being a 6th root of 10. And last one, very handy, something you definitely need to recognize is when you're doing a root and then you take it to the same power. For example, I'm square rooting the 3, but I'm also squaring it. Squaring and square rooting, cubing and cube rooting. They'll reduce, or I'm sorry, they'll cancel each other out. So all you're left with is whatever that radicand was in there. Let's practice using those rules. So on this first one, A, it's a fraction. I'm going to look to try to reduce. 5 goes into 125 nicely. So that's actually, the denominator will go away. And I'm just left with a square root of 125 divided by the 5 is just a 25. Oh, how nice is that? What's the square root of 25? Simply 5. Got it. All right, next one. This one's a cube root. I'm doing the cube root of a 125 squared. Now, I sure don't want to put a 125 squared in my calculator. That's going to be enormous, especially since I know that 125 will cube root nicely. So I'm going to cube root the 125 first, which gets you 5, and then square the 5. So whether you write it or not, it ends up looking like this. And then we take the squared and we put it on the outside. So this is all 5. 5 squared is 25. All right, next one. It took me a minute when I looked at this because it looks a little cluttery here, but ultimately all we're doing is we are multiplying 2 cube roots. They're both cube roots, so that's fair game. All you got to do is multiply the radicands. So x squared times x. Well, that is an x cubed. And then that's going to be a cube root right there. And looky there, cube root, cube undoes each other. We just get x. All right, last one is the root of a root. And they're both square roots, so you got to think there's a little 2 there. Remember that you multiply those, so that's going to be the 4th root of x. And then you're done. Okay. Those are just your properties again. Let's talk about that simplifying. This is where we'll spend most of our time on the radicals, is trying to break these down. So to break down a radical means to get the smallest radicand here. So I'm going to break it down with what comes out clean and nice and what doesn't. So I'm thinking, what's the square, what's the perfect square that goes into 75? Well, it's 25 times 3 gets me my 75. Okay, then I also have these variables to deal with. I've got to bring enough of these x's over here that it will square root nicely. So when you're square rooting with powers, remember they just undo each other. And so you're going to be dividing by this index number. I need to bring as many of these over that will divide by 2 nicely. So I'm going to bring over an x squared because that will square root nicely, which means I still have an x sitting there. All right, on the left, we have a 5x, that's what it simplifies to, square root of 3x. That's your final answer. Now, that's a square root. Look at your next example. This is a cube root. Process is similar. Don't forget the little cube. Everybody forgets the little cube, and then I have to take half off. Don't forget it. What's the perfect cube that goes into 24? 8. And then that's a times 3 gets me to the 24. Now, I need to bring over as many a's that will divide by 3 nicely. So since I have 4 of them, I'm going to bring 3 of them over here and leave 1 of them right there. And then now this left side, all is going to reduce to just a 2a cube root of 3a. All right, let's practice a little bit more of that reducing stuff. In class, we did whiteboards. And so really, I don't believe this is in your notes packet. So you could just do this on scratch paper. Somehow, I guess I'd like you to try these on your own before you just immediately go look at my answers here. So I'm going to have you pause the video when you've given all of them a good attempt, then come back and I'll have the work shown on how to do that. All right, so here are all my answers. Take a minute to look through those. Let me point out just a couple things. You really need to check. And oh, look at that. You really need to check. So do I really need to check. Check and make sure you get your index number putting it in here. Not if it's a 2, but any of these cube roots, did your final answer, here's a 4th root, did your final answer have that index number in it? Very common to forget that, and then I got to do a minus half. You do that very often, starts to add up. So The other thing I wanted you to notice is how I broke up this negative right here. You can take the cube root of a negative number. As long as this is an odd root, it's okay that this is negative. And when you break it down to your two parts, you want to put it in the part that comes out nice. You don't want to leave it here. And so that way, that's how I came up with a -5 on that. And then times my -3 is where I got that positive on that. Okay, take a look through them, and then let's keep moving. Now we're going to try some adding and subtracting with radicals. You can only add and subtract radicals if the radicands are the same. So these values, the two radical pieces, these two values have to be the same. So obviously in this case they are not. So we could maybe try to do some simplifying so that they are the same. So right here, I'm going to break this down. Perfect square that goes into 48. Might be tempting to write 4, but anytime 4 goes, you want to check to see if 16 does. And it does. 16 goes in there 3 times. So that becomes 2 times 4 times the square root of 3. So I have an 8 root 3. Minus, over here, I'm going to break down the 27. The perfect square that goes in there is going to be 9 times 3. So then that becomes 3 times 3, square root of 3. So it's -9 root 3. Lo and behold, looky there, we've got the radicands to be the same. Now, all you do is go ahead and work with the coefficients on those. So you're just going to do an 8 minus 9. That's a -1. So it's a -1 root 3. The radical part does not change. I'm going to leave the 1 off of it. We don't typically write the 1. It's just going to be a negative root 3. The next example here is very similar, except these are cube roots. So we're going to be looking for perfect cubes to break down. So I'll try probably an 8 and a 2. And then, oops, not that. It's still going to be a cube root there. The x, there's not enough x's to pull over into the cube root, so it's going to have to stay right there. That becomes 2 cube root of 2x minus, we're going to try the same thing over here. Perfect cube that goes into 54 is a 27. It goes in there twice. This one does have enough x's to pull over, so I'm going to go ahead and pull 3 of them over so they'll cube root nicely. One of them is left there. When I cube root this whole first part, it's going to be a 3x. The part that doesn't come out nice is a cube root of 2x, which conveniently matches this. However, this is not quite as straightforward as this example over here, because I want to take this coefficient and subtract this coefficient. And 2 minus 3x, I don't know, I can't really subtract them. Well, that just means you got to write them together and pretend they did go together. Okay, so it's a 2 minus 3x, put it in parentheses. That is my new coefficient on the cube root of 2x. Most of the time, it's probably going to play out like this, but every once in a while, they throw one like this at us. Time for you to practice. I've got some examples here. See what you can do with these. Once you've done all 3 of them, then come on back. Pause the video. Here we go. Make sure, check this. Did you remember to put your little 4 or your 3s? Check that. Make sure you're doing that. If you agree with all of these, let's keep moving. Now we're going to look at division with radicals. Ultimately, we call this rationalizing the denominator. We do not like, as mathematicians, we do not like to have irrational numbers in the denominator. They are non-terminating decimals, and so that goes on and on and on and on, and it's hard to divide by something that never has an end to it, so we keep these radicals up in the numerator. All right, so now, what we're trying to do, though, and this goes back to one of the properties earlier, we're trying to get rid of this square root of 3. And a quick way to get rid of that square root of 3 is to multiply it by another square root of 3, because what you're going to end up with then is the square root of 3 squared, or the square root of 9, which is going to come out as a nice, pretty 3. So our goal is going to be to always try to get something underneath here that's going to, the radical is going to go away. So I'd say that it's a square root in this example, but it could be a cube root or a fourth root. And so notice also that you don't include the 2, you're only doing the radical piece of it here. And then that turns into a 3, you get your 6. You do have to multiply the numerator, so now we're just bumping that irrational number to the top, but we're okay with that. Let's look at a cube root. Now, this one has a cube root of 5 here. 5 is not a perfect cube. So what they have done in this example is, well, you've got a 5, you kind of need 2 more 5s, and then you'd have a 5 cubed. And then 5 cubed and cube root, they undo each other, and you just get a 5. Now, you might think of it like this. I might be more inclined myself to think of it, I'll just write it over here. I might be more inclined to think of, all right, I want this to be a perfect cube underneath the radical. What will 5 go into that will make it a perfect cube? Well, it would go into 125. So let's make this be 125 by taking it times 25. Then I have 2 cube root of 25 over the cube root of 125, and the cube root of 125 is just 5. Now that's actually where they ended up over here. Do you see they eventually called this 5 squared a 25, but maybe this looks a little bit confusing with all those powers. Maybe you'd rather just work with regular numbers. Either way is fine. Let's see if you can do these two. Oh, heck, I'm just going to do it with you. All right, so here we go. You've got a 3 square root of 2. So it's a square root, so I know that I can just take it times another square root of 2, and that's going to come out nice. I'm going to have a 5 square root of 2. This ultimately is the square root of 4, which is just 2. But I'm not going to do that every time. I'm just going to start knowing that when I take 2 radicals that are identical to one another, 2 square roots, they're going to undo each other to just getting a 2. In this case, times that 3 is a 6. All right, let's look at B. Now it's the cube root. Okay, little kind of similar to the last one, but a little bit different. I'm going to do it kind of that second method. I'm going to say, all right, 25 would go into 125. And I like 125 because it's a perfect cube. So I would have to take the 25 times a 5. So I do that in the numerator as well. So then you're left with this cube root of 5 over a cube root of 125 again, which I know is just 5. Final answer right there. This one looks a little different. Now I have an addition sign between here. That makes a difference. This is a little bit trickier of a scenario because I can't just take this times the square root of 7 now, because that would be multiplied by that entire denominator. And whereas this would play out nice, that radical is just going to end up over on the 3. And then I'm still going to have it in the denominator. That means I've got to do something other than just take it times itself. I guess I'm just going to undo all that stuff. What we want to do is we want to multiply by the conjugate. The conjugate, remember, is going to be the identical same binomial, but with a different sign. So it's going to be 3 minus square root of 7. Also do the numerator, 3 minus square root of 7. In the denominator, I'm going to FOIL. 3 times 3 is a 9. Outer is going to be minus 3 root 7. Inner is a positive 3 root 7. And last is going to end up a negative 7. This right here is going to happen every single time. It's the whole reason we chose the conjugate. When you multiply these, the outer and the inner always cancel. And what that's going to manage to do for me is get rid of my radicals then. This is going to go away, this is going to go away, and I just have the 9 minus 7. but I still have my numerator. And I'm going to have to take this 2 and I'm going to have to distribute it. That's going to be a 6 minus 2 square root of 7. And one more time, 6 minus 2 square root of 7. It's going to be over 2. And normally we would just be done. However, I actually have 2 values here. The whole quantity is getting divided by 2, but I can separate the parts out, especially since this divides by 2 so nicely, and so does this. If that happens, then you do want to go ahead and keep reducing. So the 6 divided by the 2 would get me a 3. The 2 root 7 divided by 2, the 2's would reduce out, and I would just have the negative root 7. Final answer. One more. This one is for you, but it is also different because it now has 2 radicals in the denominator. So see how that's going to affect. You're still going to multiply with a conjugate. So I'm going to let you do that. Pause the video, see how far you can get with this. All right, worked out very similarly. It felt like those radicals were going to get caught up there, but they didn't, because when I did first, it really just goes away. Now, I did go ahead and show the outer and the inner. This is totally optional. Once you get the hang of this and you realize that the whole point is for the outer and inner to cancel, why bother writing it? Let's just do first, and it'll be minus last. All right. Hope this helps. Good luck.